Welcome back to 204G Part 2 on single motor control pilot devices and symbols, where we will be going over the last 4 objectives within this module. In Objective 5, we're going to look at the two most common types of control circuits that I can have, being low voltage protection and low voltage release, and we're going to discuss where and when and why we use either one of these two. Let's start by talking about low voltage protection. This is my typical 3-wire control circuit, and it's called low voltage protection because when the voltage gets low enough that I no longer have that seal-in voltage on my contactor, it's going to release the contacts. As soon as it releases the contacts, it's going to open up the holding contact, which interrupts my running circuit for my actual motor contactor. With this type of system, anytime I have a power outage, it's going to interrupt the entire control circuit, and it will not allow it to restart until you physically go over and press the start button. We use this in industrial processing where there's an inherent risk of either injuring people or damaging property by having the machinery automatically restart. In comparison to that, we also have the low voltage release. Once again, when I have voltage getting too low for the motor contactor to continue holding the contacts shut, I will have that motor contactor drop out. So in the case of a power outage, obviously I will not have any power to hold in that contactor. However, the low voltage release system uses a maintain switch in order to energize my coil. This means that when my voltage is restored, I will still have contact through that switch and my motor contactor is going to automatically restart. There's two things to know about this. First of all, I cannot use this type of system on anything that can have an inherent risk of danger. If somebody can get hurt or if I could damage property, I don't want to use this type of circuit. I have to make sure that my machinery is inherently safe either by location or by mechanical protection, so nobody can get their fingers into where the motor is. That's very important. The other thing is I only want to use this type of system on things where I want that automatically resetting system. Think of sump pumps or septic tanks or things like that where the risk of not having that system automatically restart is worse than the risk of having it automatically restart. Imagine if your septic system backed up and you had refuse coming back into your house. That would be a lot worse than anything that could possibly happen if that motor to automatically restart. So here we go. Comparing protection versus release. Low voltage protection requires a manual restart when voltage is restored. We use it for machines that have exposed moving parts. Anytime that we have machinery that could cause serious injury or damage, we want to use a low voltage protection circuit, and this is typical for most industrial machinery. Low voltage release, it will auto reset the circuit when the voltage is restored, and therefore we can only use it on circuits that are inherently safe, either by design or location. The auto restarting of the circuits will not cause any damage or injury normally, and the risk of auto restart is lower than the possible damage of it not restarting. So make sure you go over the differences between these two types of circuits and you understand where and when we would use each one. In Objective 6, we're going to look at determining what the cause of a malfunction in a motor control circuit is, so troubleshooting. And in my opinion, this is the most important practical skill that you can develop for your career. When it comes to troubleshooting motor control devices, there's typically two different types of meters that are going to be the most useful to you, and that's going to be your ohm meter and your voltmeter. So make sure you have them both on hand when you're troubleshooting circuits. With our common 3-wire control circuit, there's really only 7 different devices that could be causing us issues. Now, if we know what to expect when we use our voltmeter and our ohm meter on these devices, we should be able to narrow down the suspects of what is wrong with the circuit fairly quickly. To look at a couple different ways to analyze a motor contactor when we have the most common problem with it and simply that the motor won't start. First thing that we should do all the time is double check our voltages. Check line 1, line 2, and line 3. Check within each line, from line to line, and also from line to ground on each one of those legs. We want to make sure that no fuses are out and we have voltage coming in from our primary system. If our voltage to our system is fine, then our next step is to turn everything off because now we're going to use our ohm meter to double check all of our different devices. And here's a list of the things that we want to check. Very first thing, we want to check for any loose connections. Go through all the different screws coming into the contactor, coming out of the contactor, where the contactor and the overload are meeting. Make sure you check those screws as well. Check your holding contacts, check your overload contacts, check your switches, check your push buttons, check every screw that you can find. Make sure they're all tight. It's actually surprising how often you're going to find a loose wire that's causing you a lot of issues. The next thing we want to check is the push buttons. We want to check these for functionality, so we're going to remove them from the system, so unwire the push buttons and check them with your ohm meter. When the switches are supposed to be open, we should get infinite ohms. When the switches are supposed to be closed, we should get 0 ohms. If you get anything other than that, now you found your problem. The next thing we want to check is the coil. With the coil, depending on the manufacturer, we could get any different results on our ohm meter. What we're going to expect to find is some sort of resistance. It should not be 0. It should be anything but 0. And whether it's a 100 ohms or 200 ohms, depends on what the manufacturer has built for that coil. Remember, it's just a piece of wire. Lastly, we're going to check our overloads. We want to check to see if the overloads have been tripped, and if they have been tripped, we want to find out why they were tripped. And we want to resolve that issue first. Make sure that there's no excessive load on the motor, and then when you're sure that everything is free and clear, you can reset the overloads and see if that rectifies the problem. By the time you've checked the voltage and you've checked the ohm rating on all your different devices and you've checked your motor overloads, you should have found the problem by now. So this is a nice, simple, safe way to check your entire circuit to see where the initiating problem is. And once again, check the simple things first. Check the voltage, check your screws, and then start checking your devices for individual functionality. An alternative to solution A is solution B. Solution B, I do caution you on. I know it's a very popular one for people to just go ahead and do this, but if there's something wrong with the motor that's going to cause a problem, you could actually damage the motor more by operating solution B here. The way solution B works is first thing that we do is to verify the line voltage. If we have the proper line voltage on line 1, line 2, and line 3, both between each other and also each line to ground, then we can simply engage the manual override on the relay itself. And that's pushing down on that center armature to make sure that we physically close those contacts. You have to remember this is going to close my power contacts as well as my holding contacts. If the motor starts and holds, then we know that the fault is going to be in the start circuit and we can start checking all the buttons within that circuit. If the motor is going to start but it does not hold, then we know that the problem is going to be in the holding circuit. So now we can check our holding contacts. And if the motor doesn't start, the fault is either going to be inside the stop circuit or we have tripped overloads. Based on the information that we get back from what is actually happening with the contactor as we manually push down on the armature, we can determine very quickly where the problem is going to be. But just keep in mind that if there is something wrong with that motor, then that could damage the motor or the parts that are attached to it. So be very cautious if you use solution B. It is a good idea to disconnect the motor before you use this solution to make sure that you don't cause any further damage. Both Objective 7 and Objective 8 are on different types of pilot devices. Objective 7, we're going to look at maintained and momentary. Objective 8, we're going to look at automated switches. By this point in time, you should know the difference between a maintained switch and a momentary switch. A maintained switch is any switch that you put into its position and it stays in that position until you physically move it again. And we can see this in a number of different ways. On the screen, we have a selector switch that we use for a hand-off auto station, as well as we have a maintained contact push button, which is similar to the ones that we use in our labs as an emergency shutoff. When you press the maintain contact push button, it stays in the depressed state until you pull it, and some instances you have to turn the handle in order for it to pop back out. You can also recognize maintain contact pilot devices just by looking around your home. Every light switch that you have in your house is a maintain contact. These type of devices are any device where you have to physically change their state. In contrast, we have our momentary contact devices as well, and we can recognize these from a lot of the labs that you guys have done at the college already. Any momentary contact device is any device where as soon as you relieve the mechanical pressure on, it returns back to its original state. For us, push buttons are the most common type. However, we can also have the same thing with the joystick controller. A joystick controller can have multiple different momentary contacts within it, depending on how many different directions that we can go with it. And we see these most commonly on heavy equipment. Our last topic is to discuss some of the basic operations for our automated pilot devices. We can find automatic pilot devices in a number of different systems that we use every day. The definition of an automatic pilot device is a device that will automatically detect a change in a condition and will open or close contacts in response to that change. Our pilot devices will respond to a number of different conditions, including temperature or pressure or even the physical positioning of materials. If we use electronic devices such as our photoelectric, our inductive, our capacitive, and our ultrasonic devices, we can use all of these as proximity switches to determine how close something is or in order to activate things like lights. In your modules, you should be familiar with a bunch of the symbols that we use for our automated controls. One thing that we should be aware of is that each and every one of my automated controls can have either normally open or normally closed or even possibly the combination of both. And we should be able to recognize what they are and how they're working. Our limit switches are typically used for proximity switches and they will measure the amount of travel within our equipment. Our pressure switches are usually used for monitoring air pressure, such as inside our air compressor, or for air-proofing switches. Our temperature switches are heat activated, and we have a number of different types for different applications. Our flow switches are used for measuring our liquid levels. When we are planning out circuits for motor controls using some of our automated switching, we need to first determine what kind of function do we want to achieve, and then we have to choose the correct switch and the correct type, whether it's normally open or normally closed, in order to do that. Two of the most common ones that we have is a pump control circuit for either filling or emptying a tank, and then we have a compressor control circuit, which is going to start and stop depending on what the pressure limit is going to be. Let's look at the example of a water tank. Here we want to design a circuit that's going to fill the water tank when the water tank gets too low. So this will be an automated system that will automatically refill my tank. The first thing I want to do is determine what type of switch I use. And I really have only one option when it comes to a water tank. It needs to be a float switch, which is going to be opened or closed depending on the level of the water. My switch options are going to be either a normally closed or normally open float switch. So I need to think about the operation that I have. The goal is to be able to fill the tank when the water gets too low. So when the water comes down to the switch, I want that switch to be able to close in order to start the motor, and then it will refill the tank again. Keeping that in mind, a normally closed float switch is the way I want to go. This way, when the water gets down, it closes the switch which starts the motor. I'm going to use a 3-wire control with this circuit, so I'm going to need 2 separate float switches. One at the top of the tank, which is my high level switch, one at the bottom of the tank, which is my low level switch. And I need to determine which one of these is going to be my start function and my stop function. Since I want the pump to start, if my tank is getting too empty, the one at the bottom of the tank, my low level switch, is going to be my start switch, which makes my high level switch my stop. With this function, as soon as the water comes down to the level where it's below the low level switch, it's going to close that switch, which starts my motor contactor, and it closes the holding contact. This is going to allow my pump to start filling the water back in, which is going to open up my start switch, but since that is being bypassed by my holding contact, I'm okay with that. It's going to continue to fill the tank until it reaches the high level switch, which will open that switch, thereby shutting off my motor. This ensures that my tank is always going to be refilled whenever it gets too low. We can take all the same components and just by changing out the switches and which ones we're using for which function, we can completely change the function of our system. Take, for example, our water tank is now going to be a drain circuit instead of a fill circuit. So now once again, we have to choose a float switch, and we can choose either normally open or normally closed float switch to do this function. So first thing, think about what we want it to do. Now with this example, when the tank gets too full, we want the tank to automatically empty. And we would use this in places like sump pumps and septic fields where once the level got too high, we'd want to be able to pump it back out to drop the level back down to a safe value. Since we want our motor to operate when the level gets high, we want our switch to close as the water level comes up, which means that we are going to be using our normally open float switch this time compared to our normally closed float switch we used last time. The other thing that's going to change is since now my activation is going to be when my liquid level gets too high, my high limit switch is now going to be my start switch, whereas my low limit switch is going to be my stop. Now as this tank fills, It closes my normally open float switch, which activates my motor contactor and closes my holding contact. Then the liquid level is going to start to drop until it reaches my stop switch, which is my low level, and as it opens up my low level float switch, it's going to stop the motor control circuit. Now you can see how choosing not only the proper switch, but also the proper function of the switch can completely change the operation of our circuit. And keep in mind which one is going to be start circuit and which one is going to be stop circuit, and whether or not they should be open or closed based on the function that we have for our circuit. You've now reached the end of 204G, so return to Blackboard and complete the self-test, and then you can continue on to 204H.